Just like our last example, I'm going to start off by drawing a graph of these two curves. I've got f of x equals 3 minus x and g of x equals 5 minus x squared. So f of x equals 3 minus x is a line. So this is the line negative x plus 3. That means I've got a y-intercept of 3 and a -1 slope. So I'm going to say my y-intercept is 1, 2, 3. And I've got a -1 slope. And I know that means I'm going to go down one to the right one and so forth. So I'm just going to kind of sketch in a line with approximately a -1 slope. Sometimes you can get away with doing a really quick sketch like that. So we'll see if that works here. G of x is 5 minus x squared. Again, for a quick sketch, I'm going to think of that as -x squared plus 5. If we remember our transformations from forever ago, that's going to be the x squared graph. The negative flips it upside down, and the 5 moves it up 5 units. So I'm going to have up here at 5 this parabola hanging downwards, this vertex at 0, 5. So I'm just going to draw myself a -x squared shape. All right. So we can see now that I've drawn the graph why they didn't give us an interval. So there's a very clear spot where we have area between these two curves. It's where these two curves intersect. So I'm going to shade that area in. All right, and clearly our top curve is the parabola and our bottom curve is the line. So we're going to set up our integral, always doing top minus bottom. So parabola, which was 5 minus x squared, or -x squared plus 5, however you want to write it. And then we're going to subtract the line. So minus parentheses 3 minus x dx. The hard part perhaps on this one is going to be to figure out where those limits are. We need those x coordinates that are at the intersection points. And so I need this value and this value, those x coordinates where they intersect. So it's possible if we had been a little bit more careful about plotting some points when we graphed these two curves that we may have accidentally stumbled on those x coordinates where we had exactly the same point on the two graphs. If you don't accidentally stumble on them, or maybe if they're not at whole numbers, like they're at 1/2 or 3/4 or something, it's not obvious by plotting points, you might need to use some algebra to solve for them. So the idea here is that we're looking for the points on this graph where the y coordinates are the same, really the x coordinates as well, but we want to know where these two functions are equal. So you're going to take these two functions and set them equal to each other. So we're going to take 3 minus x and set it equal to 5 minus x squared. And that's going to be a quadratic equation to solve. So we're going to put our algebra hats on. I'm going to add x squared to both sides. And I'm going to subtract 5. And that'll get me 0 on the right-hand side. Remember, anytime you're solving a quadratic equation, you really need 0 on one side. So I'm going to have x squared minus x, and let's see, 3 minus 5 will give me -2 equals 0. And however you want to solve that quadratic formula, or factoring are probably the easiest too. Let's see, I think this one will probably factor. And I need a 2 and a 1 to give me that -2 at the end. And I need the 2 to be negative and the 1 to be positive, so that when I multiply that all out, I'll get a -x in the middle. All right, so let's set both of those equal to 0. X plus 1 equals 0. X minus 2 equals 0. Subtract 1 from both sides here and add 2 to both sides here. So I get -1 and +2, and that looks consistent with what I've drawn on my sketch over to the right. All right, so those are going to be my limits, -1 to 2 on my integral. So I think on this one, the graphing in the algebra is possibly more difficult than the actual calculus we're going to do. So let's go ahead and clean out this slide, and then we'll evaluate our definite integral. All right, so let's distribute our negative sign in our integral. We've got the integral from -1 to 2, 5 minus x squared minus 3 plus x dx. -1 to 2, and I've got -x squared plus x plus 2. All right, so let's find our antiderivative here. I'm going to have the negative goes along for the ride, add 1 to the exponent, and divide by the new exponent. So x cubed over 3. I've got x to the first, so x squared over 2. And antiderivative of 2 is 2x. And we're going to evaluate that all from -1 to 2. So lots of arithmetic coming. So I've got the negative, then I'll have 2 cubed over 3 plus 2 squared over 2 plus 2 times 2. All of that minus what I get when I plug in -1. So -1 cubed, it's a lot of negative. And then -1 squared over 2 plus 2 times -1. All right, so I've got in the first set of brackets, -8/3. That's going to be 4/2, so that's just 2 plus 4. And then in the second set of brackets, let's keep track of our negatives here. So I've got -1 cubed, that's going to be a -1, but then that's going to cancel out with this negative here. So that term is going to be positive 1 divided by 3. Then I've got -1 squared, that's a positive 1, so I'll have +1/2. And then 2 times -1 will be -2. All right, so I've got -8/3 plus 6. And then let's distribute a negative sign through the second set of parentheses. So -1/3 -1/2 plus 2. And let's see, I got some stuff I can combine. So I've got the -8/3 and the -1/3. That's going to give me -9/3. I've got some whole numbers. I've got 6 and a 2. It's going to give me an 8. And then I've got -1/2, which isn't going to combine with anything just yet. So let's see, -9/3 is a -3 plus 8. So -3 plus 8 gives me 5 minus 1/2. Let's just turn that 5 into a fraction. So that's going to be 10/2 minus 1/2, and we get 9/2. All right, so let's chase this over to the GeoGebra applet and we'll see if we got the right answer. As I was typing this in, I learned something about this GeoGebra applet. It's important that you type the top curve in as f of x and the bottom curve in as 3 minus x, because it's always going to subtract f of x minus g of x. So you definitely want to do top minus bottom. So I had to rearrange the names of our function. The f of x is 5 minus x squared, g of x is 3 minus x, and then entered the limits -1 to 2 that we solved for algebraically. And it looks like exactly the same area that we graphed, and it gives us the answer of 4.5, which is the same as the 9/2 that we calculated. Let's do one more example here. And this one you'll notice also does not have that square bracket interval given to you. So we are going to have to figure out from our graph what our limits are going to be on our definite integral. All right, so we start off with x squared, and I know what that graph looks like, and I could do a quick sketch. I kind of got burned on the last one by not plotting points, so I'm going to do a little bit better job this time plotting points. So let's say 0 squared is 0. We know that 1 squared is equal to 1. And I know 2 squared is equal to 4. And then I've also got some stuff over on the negative x-axis side. I need the left half of the parabola. So -1 squared is 1. -2 squared is 4. And we'll fill in that parabola shape. All right, our second curve is 2 minus x. Again, if you want to think of that as -x plus 2, that's just a line with a y-intercept of 2. So I'm going to come up to 2, got my y-intercept, and my slope is -1. So I'm going to go down 1 into the right 1. So down 1 to the right 1. I actually found an intersection point there at 1, 1. Down 1 to the right 1. And just to make things more exact, I'm going to go to the left as well. So I'm going to go left 1 and up 1. And left 1 and up 1. And actually, we got some nice intersection points with this line and this parabola. So I'm going to fill this in. So sometimes you can save yourself some algebra by doing some good plotting points. This one looks like almost a flipped version of the last one where we have that area that's between the line and the parabola. We have to be very careful of how they described this particular region. They said they wanted the region bounded by the parabola, the line, and the x-axis. So if I shade this area, which kind of looks like the area they're going for, that area is not at all bounded by the x-axis. So that actually can't be the area that they're looking for. The only area that's bounded by these two curves and the x-axis is this almost triangle looking part. That's actually the region they're describing. That's the one that we need to find the area of. All right, so the limits on this one look pretty easy, right? Just from x equals 0 to x equals 2. We kind of found those by plotting points, which is good. The tricky part about this one is when we go to do the top curve minus bottom curve, the top curve changes halfway through this region. So if I'm starting off at x equals 0, it looks like the top curve is x squared and the bottom curve is the x-axis. But then once I get to x equals 1, now the top curve is the line and the bottom curve is the x-axis. So the bottom curve stays the same, but the top one changes halfway through. You actually need to do this one with 2 integrals. We need to do one integral that represents that red region and one that represents the green region, and then add them together at the end. So for the red part that I have drawn there, we need to go from 0 to 1 on the x-axis, Our top curve is the parabola, x squared. Our bottom curve is the x-axis, which is just y equals 0. Then we're going to add to that a second integral where we're going to go from x equals 1 to x equals 2. Now our top curve is the line 2 minus x, and our bottom curve is still the x-axis, which is y equals 0. All right, so these integrals are not too tough. We'll just do these two completely separately. So let's see, I have x squared minus 0. This is just the integral from 0 to 1 of x squared. And then the integral from 1 to 2 of 2 minus x. So find the antiderivative of x squared. That's going to be x cubed over 3. And we'll evaluate that from 0 to 1. And then we'll come over here and find an antiderivative here. So I've got antiderivative of 2 is 2x minus antiderivative of x is x squared over 2. And we're going to evaluate these two from 1 to 2. And you could work these two integrals out separately and then kind of put them together at the end. That would be fine as well. All right, so x cubed over 3, we're going to plug in 1. So I've got 1 cubed over 3 minus 0 cubed over 3. And then we'll do the limits for the brackets. So we're going to plug in 2. So I'm going to have 2 times 2 minus 2 squared over 2 minus 2 times 1 minus 1 squared over 2. All right, so just some arithmetic to go and we'll be done. Let's clean off our slide. All right, so I've got 1/3 minus 0. I can kind of skip that 0 cubed over 3. And the first set of brackets, I've got 4 minus 4. Let's see, 2 squared is 4. 4 over 2 is 2. So minus 2. So that's my first set of brackets. And then let's see what we've got inside that second set of brackets. We've got 2 times 1, 1 squared over 2. All right, so let's see what we can combine. I've got a 1/3. 4 minus 2, I can make that a 2, so plus 2. And then let's distribute this negative sign through the brackets. So I've got minus 2 plus a half. And my 2's actually cancel out. So all I've got left is 1/3 plus 1/2. Those need a common denominator to put together. So I'm going to change those into 6's. So I'm going to multiply by 2 over 2 and by 3 over 3. So I've got 2 over 6 plus 3 over 6, and we get 5 over 6.